this is talk about everything you always want to know about BPF, but we're afraid to ask. So don't be afraid anymore. If you want to know something and I'm not telling it, please raise your hand and I'll get back to you. I'll come to you. So I think it's about time. Yeah, well. So a little bit about me. Most people know my name, I think, and I started working in networking back in the mid-90s for an internet provider when internet in Holland was just non-existent. It was at the universities, but normal people wouldn't have access to internet. They didn't know what an email address was. And I started working for a little company, and it had grown, like, in 4 years' time, it had grown to 100 people. Like, it's the internet bubble, just before the internet bubble. And after that, I started working for a big bank, and that's where I learned what proper networking was, because in the internet time, it was just like crazy. And in that time, I started working with Ethereal because I needed to solve problems, and well, I guess you all do. And when I was working for a reseller selling or installing and configuring all kinds of network devices, I had a lot of features missing, so I started developing for Wireshark. And that's how I became a core developer, and yeah, well, I ended up here on stage. What can you tell? So I worked a lot with F5 products, doing iRules and stuff. And 6 years ago, I started my own company to focus mainly on network analysis and troubleshooting, which is great. Well, I live in Haarlem, do a little bit of diving, like some movies, and go to occasional raves, and well, that's it about me. So, BPF, Berkeley Packet Filters. Who was here in, I think it was 2011, when Steve McCann had a keynote speak? Just a couple of guys. Yeah. Steve McCann is the guy who, when he was in university, he created BPF language. So it's back in '92. So some of us are not even born before '92. I am, but that's... so he was at SharkFest telling about how he came to build BPF and why it's been built. And one of the main reasons is they needed to be able to filter it. Back in the days, it was like a hub. So every traffic on the whole network was visible. And if you wanted to follow your own session, he needed something to filter. And he came with the idea to do that, the filtering in kernel. Why? Because if you get a packet from the network card and you get it in the kernel, you need to move it to a user space, so you need to do a memory copy, then you do the filtering, and then it turns out, oh, I don't need this packet, and you throw it away, and then you have a copy action for nothing. So he made the BPF filter a virtual machine within the kernel. But then you need to control that virtual machine. So he made an interface with user space that you can load up a program to this kernel module to do the filtering. And that's basically the basics of why BPF is a very powerful and very quick filtering engine. So what happens? The user space program, like dumcap, which is being used by T-Shark and Wireshark, it creates a bytecode program, loads it to the kernel module, and that all the traffic flows are being filtered by the bytecode, and only what is allowed by the filter will be copied to user space to the program that you're using. So the main advantage is you don't copy anything that you don't need, and that makes it really quick. Then, since we're in the kernel, we have to be careful, because if something loops in the kernel, your system crashes. It doesn't do anything anymore, because there's no prevention from things in the kernel going wrong. So in the language, there's no jumping backwards, so you can only jump forward. And that's because people ask me all the time, like, what's the difference between display filters and capture filters? And why do we have capture filters? And why can't we filter on anything in capture filters? Because I really want to filter on, like, when I'm capturing, I want to filter on a cookie value. Well, to be able to filter on a cookie value, you need to look in the packet one by one until you reach the cookie. Until you reach the end of the packet. But that requires a loop, and a loop is not allowed in BPF. So if you want to know what you can filter with BPF and what you can't filter with BPF, everything that you can calculate where the information is that you need to filter on, you can filter. If you can't calculate where it is, you can't filter on it. So that's something you need to have in mind. But that also gives you a lot of power, because most of the times you are able to tell in a packet where the information is that you need. Then there's another restriction. It's a limit of 4,000 instructions. But I've never come across a single BPF program that's that long. But there's a limit in the amount of filtering that you can do. You will probably never hit it. Okay. When I was preparing for this talk, I looked up all kinds of things about BPF, and it turns out that there's a BPF revival, because there's in the Linux kernel there's now hooks, not only to the packet but to all kinds of system information, being done in the same way as BPF does it. Like there's a kernel module, and you can use programs. You can push them from user space to this kernel module, get information out of the kernel, and give it back to user space. So that's actually the second part. That's eBPF. It follows the same rules. There's a kernel with some bytecode and a user program that can access that. Another new way of using BPF is IP tables can use a little modified version of BPF, but you can use BPF filters to do IP tables filtering. That's something Cloudflare, the big anti-DDoS provider, is using. They have a nice talk, a nice blog post on it as well. Some network virtualization, network function virtualization products, they use kind of a BPF infrastructure. And also on i5 units, you have packet filters that are based on the BPF language. And one customer called in on a Sunday evening, "Oh, we're in trouble. Our site is down." So I looked into the i5 device. Could barely do anything because it was really slammed with traffic. I discovered that it was a SIM flood. And there were some specifics in the SYN packets that I could filter on with a BPF filter. So I built a BPF filter for that, put it in, and the site was back up. I got a cake the next morning. This was really nice. So how are we going to use BPF filters? Back to network packets, because that's our main interest. Why do we want to filter? Anybody? Feel free. Hansang, why do you want to filter?
Limit the size.
The size of what?
What you have to analyze.
And why do you want to limit the size of what you have to analyze?
So it'll be timely. You can do it quickly.
So you can do timelier analysis. Yeah, if people were at Jasper's talk yesterday, if you have like gigabits or maybe gigabyte or maybe terabyte trace files, yeah, you might want to keep them down if you don't. So that's one of the reasons. What's another reason? Are disks quick enough to store like 10 gigs of traffic? They're not. So it's not only that you might not have the storage, or you might have, it's also that you want to capture every packet that you're interested in. So if there's a lot of packets coming in that you're not interested in, and they make that you have packet loss, or loss in discarded packets in your trace file, then you're screwed. So overloading the CPU or the disk I/O is one of the main reasons to do filtering at capture time. Why shouldn't you do filtering? Anyone? You? You might filter out interesting data. If you're solving a problem, it's usually like the haystack that you don't know where the needle is. So you don't know what the needle looks like, so how can you filter on the needle? So you want to filter on things, you don't want to filter out things that you might end up needing to solve the problem. You might miss important packets. So for me, the best strategy is don't filter at all if you don't need to. If you can, if your capture system is quick enough, has enough storage, do the filtering later on. Unless, like Jasper told us yesterday, if it's too much to be post-processing the data, then you might want to filter also while capturing. If you're not interested in the payload, if you don't need it for performance analysis, use a snap length. Just slice the packets and store only the headers. Another strategy, if this doesn't work, is just filter out what you don't want to see. I was at a telecom, I'll come back to that later. A lot of times there's a lot of traffic in your trace that you can identify, and you know for certain that that traffic is not of interest for your problem. filter that out. So you keep all the unexpected traffic. If all else fails, then specifically filter for what you need to see. Like if you're analyzing a website and you can filter on the website server address, most of the time that will work. So an example of reducing the packets is I was at a telecom company, and they had like all kinds of encapsulated packets, and they really wanted to know, only want to filter out on specific parts in those packets, but I couldn't calculate where the information was. And their capture system couldn't keep up. So I said, okay, if we can't filter on what we want to see, let's just filter out what we don't want to see. So the first thing was, this is a display filter. I opened a little trace file in Wireshark and then started working in it. There was some SCTP traffic, just some updates every like second or milliseconds. I don't know how often anymore, but it was a lot of traffic. There were 20,000 frames of that. So I created a BPF filter to filter out that traffic. Then I saw a lot of VRP traffic. They had lots of VLANs. Every VLAN had VRP, so there were a lot of VRP packets. I filtered those out. Then there was DFD. So there was all kinds of protocols that I could identify, create a capture filter for it, and then in the end, out of the 50,000 packets, only 7,000 remained. So that's an 86% reduction. The same goes for the amount of bytes, almost 83% was reduced. Well, the final filter was a little bit complex. So how can we make such a filter? That's what this session is all about. I'm going to teach you that you can read this I hope you can read this at the end of the session. Another reason to do BPF filtering that you might not think of, and it's what Jasper told us yesterday also, is performance. If the display filter works like, okay, I have this packet, I'm going to fully dissect what is in there. I want to know everything about the packet, and then I'm going to filter. BPF works the other way around. BPF says, okay, I have this code, I know where to look. As soon as I have found something that would break my match, I'm done with the packet, next packet. And it looks at specific places, so it's very quick. So the first mismatch will make the packet go away and go to the next packet. And so BPF filtering and post-processing is not currently possible in the Wireshark toolset, which is a shame. It's something I might want to work on, because I think it can be very handy to have like also not only a display filter in Wireshark, but also a BPF filter engine in Wireshark. Who would want that? Only one? Okay, I'll don't do it then. Sorry, Hansang. Okay, so that's something but there are other tools. You can use TCP dump or WinDump if you're on Windows. When I need to filter like a very large trace set of, and I want to filter for certain IP addresses or certain conversations, I run it through TCP dump first and then go to Wireshark. Okay. So what is this BPF virtual machine then? Steve McCann created it with a Motorola 6502 in mind. I'm a Commodore 64 user way back, so I know this processor. And so there's an accumulator. That's just a field that you can use for calculations and reading data out of the memory or out of the packet in this case. But the memory model is packet-based, so where you normally have memory with programs and data and stuff, the memory model of this machine is every packet will be the memory that the machine gets access to. There's a lot of ways that you can address the data, that you can retrieve data from the packet. I'm going to show you later on. And there's some calculation and arithmetic logic, so you can do calculations on information from the packet as well. In the end, this is what's being pushed to the libpcap filter engine. It's a bytecode. It's just, this is an instruction. This is a jump true, jump false, and some extra information needed to do depending on the opcode that you're using. I can't read this, fortunately. So there's I can't read that, but I can read mnemonics. So these are all the instructions that are available. with all the addressing modes that are available. You can get this from the BPFC mem page. I'm going to talk about that later. And it will create such a, the bytecode that you just saw is actually this BPF program. This is something I can read. Well, I can, you can learn it too. There are instructions with some addressing mode and some jumping whether something is true or false. It's a very basic machine. So this is what we're going to look at, but this is not easy. And that's where the BPF filter language comes in. The BPF filter language is being designed by... Okay, I'll give you a second. There's also one about Uncle Jack. The BPF filter language is a language that is easy to type, easy to remember, and very powerful. And the BPF filter language is being turned into this bytecode or these mnemonics, and then it's being handed over to the kernel. So it's a filtering expression, and it takes one or more primitives, and each primitive is an ID with some qualifiers. Like, I'm going to show you some of these later on. There are 3 different kinds of qualifiers. There are type qualifiers, so that's kind of it's an ID name or a number. Sorry, the ID name or a number is the ID, but the qualifier is like host 1.1.1.1. The host is determining what kind of information is the 1.1.1.1. Then there's a direction qualifier, source host 1.1.1.1, or a protocol qualifier, ether host, and then it's not 1.1.1.1, but you can add a MAC address to that. Then there's logic, and, or, and not, to combine all those primitives into complex filters. And to save typing, you can omit duplicates. So if you have host 1.1.1.1 or host 2.2.2.2, you can just say host 1.1.1.1 or 2.2.2.2. That's not funny. Okay, and there's all kinds of arithmetics to help you in that way. So what are primitives? This was the most difficult picture to... What kind of picture do you do with primitives? But I found one.
It's perfect.
Yeah, I think it's nice. What primitives? They usually consist of an ID. Oh, I already said that. The qualifiers. Oh, that's like something double. So some examples. Host SharkFest.wireshark.org this is a qualifier and this is the ID, and together it's a primitive. Source host, again, a direction, a type, and an ID. And then you have the ether source host. So this is the protocol, the direction, the type, and the ID. So all these examples are one primitive. So then you can combine those to create complex things. You can use AND or the double ampersand to concatenate things. It means host this and port that. It both needs to be true. With OR, of course, either one of them needs to be true. With NOT, it doesn't. It needs to be false. And you can add up things, combine them with parentheses. So that gives an example like, what will this do? Will it show you traffic from both hosts or just between those hosts? Actually, both primitives need to be true, so there needs to be an IP address with 10.0.0.1 and the IP address with 10.0.0.2, so it's traffic between those two systems. Or you can do OR when you want to see traffic to either of those systems. Or you can make it more complex with putting a UDP port and a TCP port in it. This might not give you the results that you want, because there isn't, it says it needs to be this host and that host, okay, so it's traffic between those two, and UDP traffic on port 53, okay, so it needs to be DNS traffic between those two, or that host and that port. So what is the logic, which order will be followed? And that's not totally true in the language. So please use parentheses to make sure that you do what you want to do. In this case, I need all traffic from this host to the DNS server or to the web server, which is different from what I told you earlier. So use parentheses a lot. Even if you don't need them, make it clear for yourself, use them. Then, what I said, you can omit duplicate qualifiers. It saves typing, mostly. So this TCP port 80 or TCP port 8080 will turn into TCP port 80 or 8080. This will be host 1. And this one, can we combine this in any way? We can't, because they're not identical. They're not identical qualifiers, because the direction is not the same. So be careful to combine them when the qualifier is not the same. Then how do you get to specific bytes in a packet?
Where did you get that one? I love it.
Google is your friend. Yeah, I didn't want to do only text on my slides this year, so you're stuck with the pictures. So you can use these brackets to address certain bytes within a packet. And where does it look for those bytes? Starting at the type. So if it's bound to TCP, it will calculate first where the TCP header is, the first byte of the TCP header, and then from that point on, offset 13, which in our world is the TCP flags. So this filter will filter on any TCP SYN packet. From the IP header, the start of the IP header, at position 8, we have the IP TTL. So this would filter on all packets that doesn't have, that probably, because it's not, normally when the system sends out an IP packet, it has a TTL of 64, 128, or 255. If you tweak your system, you can do it differently, but most systems follow these rules. So this would mean any packet that hasn't been routed yet. Can we combine it like this, because we saw there's the same qualifier, so we should be able to combine it. Unfortunately, that doesn't work. So there's kind of some bugs or inconveniences in BPF as well. But it will tell you it doesn't work, because it will give you a syntax error. You can also get 2 bytes or 4 bytes this way. So you can, if you want to check on an Ethernet address, just check the first 4 bytes and then the second 2 bytes, or the remaining 2 bytes. But you can't do it like this. You can't get 6 bytes at the same time. And that's because this little machine, this little virtual machine just has instructions for getting a byte, a half word, or a word. And it's a 32-bit machine. So that's why you can only use slices like this. Then if you get to certain bytes, you also might want to check certain bits. You can use the logical AND. So remember that when we use the AND to combine primitives, it is a double AND, a double ampersand. In this case, it's a single ampersand, so this is a bitwise operator. You can extract 1 or more bits. So if I'm going to check for the OUI, I get the destination. So from the Ethernet header, the first 4 bytes are the first 4 bytes of the destination MAC address. But I'm only interested in the first 3 bytes of those. So I end with 6F and then 2 zeros. And it will give me only the first 3 bytes plus, of course, a 0 for the last byte. And I can check that whether this is my MAC address of my Apple, so I can check if it's an Apple MAC address this way. You can use a logical OR to combine bits, and that's mostly useful in the next instance when some fields do have some names attached to them. So if you don't know what the offset is for TCP flags, you can do TCP and then use offset TCP flags. I kind of find 13 easier to remember than TCP flags. It's also quicker to type. So, but this means get your TCP flags, then look at the SYN bit and the ACK bit, and I'm ORing those, so I'm filtering both bits. And if I extract those bits, I only want the TCP SYN bit to be true. So this actually filters on only SYN packets and not SYN ACK packets. If I left this out, it would have been SYN and SYN ACK packets. The same goes for ICMP. They have some words, some definitions as well. So you can filter on ICMP type or ICMP code. And then for ICMP type, there are all kinds of words. You can look them up if you look the man page of the PCAP filter. You can look at it in the internet or on your own machine. So. Then all the arithmetics. You can do calculations, not only on the values, but also on the indices. So if you want to slice something, you can do a calculation within the slice brackets. Standard, you have like plus, minus, multiply, and division. You have right shift, which means shift all the bits one place to the right, or your right, which means actually multiply by 2. Or a left shift, which means divide by 2 and drop the remainder. So some examples. You see that the filters are getting a little bit more complicated now. Starting from the start of the TCP header, I'm looking for 4 bytes at this offset. So what's the offset? I'm looking at the 12th byte, which contains the TCP header length in the high order nibble. So the high order 4 bits is actually a 4-bit counter that counts the amount of words in your TCP header. So if I extract only the 4 higher bits, and so I need to divide it by 16 to get the value, but since it's counted in words, I need to multiply by 4 to get the amount of bytes. So basically that means dividing by 4 or right shifting 2 bits. So this calculates the header length of my TCP header. Then so from the start of the TCP header, going so many bytes as the TCP header is long forward is actually the start of the TCP payload. And I'm going to check at the start of the TCP payload a GET space. So you can check it, get request. Yes?
What if does this take into account VLAN tags, IP options in the header, and TCP options for these counters?
So you're saying 3 things. VLAN tags, it doesn't take it into account, and we will see later on why. IP options, it does, because to get to the start of the TCP header, BPF knows how to calculate the IP option length. So yes, that's incorporated. For the TCP header length, that's what we're doing ourselves, calculating what the TCP options are doing. So yes and no. It depends. What does this filter do? So at the second position in the IP header is the total IP length. So that's the length of the IP datagram. Then this is the calculation of the IP header length. And this is the calculation of the TCP header length. So if I calculate the total length of the IP datagram minus the IP header length minus the TCP header length, it's the length of the payload. So this actually tells you, gives me all packets where there's a payload. So drop all the X, drop all the fins, the SYNs, the resets, just give me payload data. Or you can do it the other way around, say, okay, I want to have all the X or the, so. With calculations, you can do a lot in getting things done. Then, like you said, a VLAN tag, how does VLAN tags come into the place with BPF filters? Well, every time BPF encounters the word VLAN, It checks for if it's a VLAN, but it also increases the offset for the rest of the filter by 4. Why? Because the VLAN tag is 4 bytes. So you can do VLAN 10 and host 10.0.0.1. Give me all packets where there's a host 10.0.0.1 with a VLAN tag of VLAN ID 10. But this will not work. And why? It's because VLAN 10 or VLAN 20 means I'm going to look for VLAN 10 and advance all the filters, all the offsets by 4. And again, I'm going to look for VLAN 10, but the offset has been put away 4 bytes. So this will actually look for a Q and Q tag with VLAN 20. So this filter means give me all packets with a single VLAN tag in VLAN 10, or all other packets with a Q and Q tag where the innermost VLAN tag is VLAN 20. That's not what you expected. I'll come to an example how you can solve this later on. The same goes for MPLS. MPLS does the same thing. It increases all the offsets by 4. For PPPoE, there's a PPPoE header of 8 bytes, so it increases the offset by 8 bytes. It does that only once, but I don't think there's any logical traffic where there's multiple PPPoE headers inside one packet. So that's why it's doing it differently. So now that we learned a bit about the possibilities of the filter language, what does that mean if we look at the mnemonics? Because you can build a very complex filter, but if you don't know what it does it filter the right thing? And that's where the mnemonics comes in. Build your filter and check whether it's correct. If you can read the mnemonic code, you can check whether the filter actually does what you intended to do. You don't need it for IP host this and TCP port that, but if you're building complex filters, you might want to look at the code to catch some errors in your filter language. In Wireshark, you can use the compile selected BPFs. It will show you the filter code after you type in the capture filter and click on the button. Or you can use TCP dump with -d to do the same thing. If you really want to check your bytecode, you can do -dd, but I won't recommend that. So this is what a bit of machine code looks like. So I'm having a filter, IP, and host 1.1.1.1, and TCP port 80. And I'm using a snap length of 128 bytes. This is the filter, and I'm going to run through the whole filter with you to see what it does. So this is my packet. Starts with 6 bytes of Ethernet destination, 6 bytes of Ethernet source, then an ether type. So the first part that the filter does, because I told it to check for IP, is it loads half a word, so 2 bytes, from position 12, which is the position of the ether type. It compares the value with 800 hexadecimal, which is the ether type for IP, and it will say if it's true, jump to position 2, which is on the next slide. If it's false, I'm done. It's not IP. I don't need to check the rest of the packet to know whether I need to filter it or not. So it goes to the last line, line 16, return 0, which means don't capture the packet. Or don't show the packet, don't save the packet, depends on what your filter does. But the filter doesn't match. Second line, or the third line actually, load, which means load the whole word, 32 bits, from position 26. At position 26, there's the IP address. So this is also why if you have tagged and untagged traffic, you need to do something yourself to make that work, because it just checks at specific offsets. So if it's non-tagged traffic, it will check at position 26 and will look for 1.1.1.1. This is not 1.1.1.1. So I'm jumping false, I go to position 4. If it was true, I go straight away to position 6. But I need to check the destination IP address. So at position 30, I'm checking again for 1.1.1.1. If it's true, I also go to 6. So either the source was right or the destination was right, I go to 6. If both are wrong, I again go to drop the packet. Then it needed to be TCP traffic. So I need to look at the position of the TCP, the IP protocol. That's in position 23. So it loads a byte from position 23, compares with 6, which is the IP protocol for a number for TCP. If it's true, I go on. If it's false, drop the packet. This is the most complicated part from this filter. It needs to check for fragmenting, because if you want to check for a source port or a destination port, which we're going to do, it's only available in the first fragment of a packet. So it's going to look at the position where the fragment offset is located. Only the last only the last 13 bits of this location are the offset. So it masks the other bits, and then it checks whether it's set. That means if it's 0 or non-zero. If it's 0, jump through. If it's non-zero, sorry, jump through, drop the packet, because it's a fragment. So if it's not a fragment and the offset is 0, go to position 10. Now we need to check the TCP port number, because we want traffic on port 80. But we don't know how long the IP header was. There can be IP options. So we need to calculate what the position of the TCP header is. There's an instruction that says load from a certain position, a certain offset, take the last 4 bits, multiply them by 4, and that's so at the position 14 is the IP header length. It's again in words, not in bytes. So, and it's only the last 4 bits that are the value. So I get the last 4 bits from this position, and I multiply by 4, and that's the IP header length. Why do I add 14? Because there's an Ethernet header in front of it. So you get the IP header length plus the Ethernet header length. Together, they're the start of the TCP header. Within the TCP header, so it calculates this and puts it, so this is being put in X, then it uses X plus 14 as a position for loading half a byte, which is half a word, which is 2 bytes, and that's the port number. At this position, it's the source port number. Again, it checks whether it's 80, 50 in hexadecimal. If it's true, then, hey, this packet matches. And it can go and return something that's non-zero, which means this packet matches. If it's false, I still need to check the destination port, because maybe that's the 80. It goes to the destination port check at 2 bytes further. If that's true, I have a match. If not, I need to drop the packet because it doesn't match anything of the filter. So in short, in total, it's this filter. So it might look scary at first, but if you read it line by line, it's actually not that scary. Why is the 128 red here and red there? The result of the bytecode is actually the capture length. So that's interesting, because if the result is the capture length, you can maybe do interesting shit. We're going to see that later on. Any questions so far about the BPF language and the mnemonics? All right. Okay. So we talked about offsets and VLAN tags and how they can disrupt things. This filter gives me all untagged traffic for IP address or for an IP host 2.2.2 or any tagged packet for host 1.1.1. You can see it checks for at position 26 and 30 for the IP address 2.2.2. Just like we saw before, it's a position of an untagged IP address. Then it will check whether the ether type is 8100 for .1Q, and it will look at position 30 and 34. Notice it's 4 bytes further than before for the IP address 1.1.1.1. So this works. If you do it the other way around, VLAN and IP host 1.1.1 or IP host 2.2.2, you will see that it will look for both IP addresses at offset 30 and 34. So this filter is not the same as that filter. This filter will look only in VLAN tag packets for either that or that destination host, even though the syntax might tell you differently. So be careful when you use VLAN tags, MPLS tags, or PPPoE tags, because it advances the offset. So you need to take that into account. So if you need to filter traffic that's been untagged, tagged, and .1Q tag, Q and Q tagged, you need to put all your filters that need to filter untagged traffic first, then all the filters that are for all the VLAN tag traffic, and then all the filters for the Q and Q packets. So how can we solve this then? If I do VLAN 10 or VLAN 20, the purpose is to give all the traffic with a VLAN tag either 10 or 20. As you can see, it will look for VLAN tag traffic. It will get the VLAN ID. Those are the last 12 bits of the 2 bytes at this position. And it will check whether it's 10. But then for the next check, you see that it uses position 16, which is the Q and Q tag. So this doesn't work. How can we make this work? Well, we do some stuff ourselves. I'm going to check for a VLAN, and I'm going to look at the position where the VLAN tag is, calculate, take the last 12 bits, compare it with 10, and do the same thing, and compare it with 11. Well, that's not 20, but you get the point. So, if you can't do it with a normal filter language, you can extend it with slicing and arithmetic and everything. So, as long as you can calculate where the data is, you can create a filter. And if you can't, you can mail me and I'll help you. A couple of times. After that, I'm going to charge you. Hey, I've got my own business. I need to. So the filter TCP length that I showed you earlier. What are the important parts? We've got the IP header length. We've got the IP datagram length. And we've got something that's the TCP length in the packet. So that's how I came to do this filter. These 2 bytes are the total IP datagram length. This calculation on this byte, it takes the first 4 bits, sorry, the last 4 bits, and multiplies it by 4, and that's the IP header length. Then it takes the first 4 bits, the higher order 4 bits of this byte, multiplies it by 4, and that's the TCP header length. Together, they form the TCP length, the payload length. And this is the code that's being generated. So again, I need to look for IP, I need to look for TCP. Then I'm going to load the total datagram length, and I'm going to store it for I'm going to store it in one of the memory positions. You've got a couple of memory positions that can be used. Then I need to calculate the IP header length. So this is all IP header length. Then I load the previous value, I subtract the IP header length, and I store it in a new memory position. Then the same for the TCP. I'm going to load. This is actually calculating the start of the TCP header. Then from that start on, I get the byte where the TCP header length is. I multiply it by 4. I get my old value back. I subtract the other value. And then if it's greater than 0, I'm jumping to returning a full-size frame. And otherwise, I drop the frame. Do you see that here I'm calculating the position of the TCP header myself, and here it's been done within, or the length of the IP header I'm calculating myself here, and here it's been done in one instruction. So there's an optimized instruction within BPF to calculate it, but it can only use it itself. If I'm doing the calculation myself, I could have used this function, but it doesn't know it. It's not optimized. So, but it works. Then capture filter on steroids. There was the ask, the Wireshark org site, somebody asked, I have SIP traffic and I have SIP traffic in an IP over IP trunk and I need to capture filter both sides of the traffic and I don't know how to do it. Well, then I got triggered because I like capture filters. So I got a packet. I think he sent me a packet, a little capture file. And I was, okay, this is the first IP header. Then I've got the second IP header, if it's IP over IP. And then there's my UDP header. So how can I filter on SIP and SIP over IP? Well, if I work it out, it's like port 5060 for SIP traffic or IP over IP. And then I need to have either UDP or TCP traffic in the second IP header. Where's the second IP header? Well, position 20 plus 9 relative to the first IP header. Because it's the second IP header, 20 bytes extra plus 9 bytes for the protocol. And then within that header, within the payload, I need to look for those ports. So it's 20 bytes for IP header. It's starting from the first IP header, 20 bytes for the second IP header, 20 bytes for the TCP header or UDP header. No, this is the second IP header. And then on that position, get the bytes. What it doesn't do here is calculate the proper IP length, because there can be IP options. So if you want to take into account the IP options, you need to make it more complex. That's where it gets like really freaky. And so it worked, but it's not something you want to do every day. But if you really need to filter, know that you can. And this is the final BPF program that filter created. How am I doing on time? Till when do I have? Like half an hour still, right?
You're at 11:15.
Okay, then I'm going too quickly. Because this is almost my last slide. So lots of Q&A. Maybe some demos.
Say demo.
Yeah, demo time, yeah.
Stick yourself.
All right, taking it one step further. Like we've seen that we can build filters with normal filtering language, and it creates a nice BPF program. And we saw, okay, the return value is the capture length. Why not make a filter that has a different capture length for different protocols? So there's now BPFC, BPF compiler. It's in the netsniff ng toolkit. And you can write programs in the mnemonics and then compile them into BPF bytecode. You can use it as a filter in capturing, but unfortunately not within Wireshark yet, because you can't load a bytecode filter into Wireshark, but you can load a bytecode filter in netsniff ng. So you can filter on. Why do we want to use it? You can optimize filters, because what you saw earlier is that the filter wasn't optimized, the complex filter wasn't optimized, so you can optimize filters if you really need to have extremely high speed. Or stuff that's not possible by just using the filter language. This is something I want to work on, because it would be nice to have dumbcap read bytecode filter, so you can just create a bytecode filter and give it to dumbcap. But netsniff ng tools can do it. So I used the netsniff ng tools to create, to compile a filter, and that's something like this. So this is the code that I wrote myself, based on code that's been exported by using normal filters. I can have comments in here, and instead of all the numbers that you saw before, you have labels. You can create labels to jump to. And so again, I'm looking for the ether type. If it's .1q traffic, I'm going to do something with .1q traffic. If it's IP, or is it not? If it's not IP, so it's not VLAN traffic and it's not IP traffic, I'm jumping to position pass 14. Pass 14 means return 14 bytes, just the Ethernet header. So we'll capture just the Ethernet header. Then I'm looking for, let's see, the IP header length. So if it's If it is IP and, okay, I need to, okay, so I'm calculating the IP header length, I'm adding 14, and then I'm jumping to, it's a layer 4 packet. So I'm going to check at the layer 4 whether it's TCP or UDP, jumping to UDP if it's UDP, I'm adding 8 for the UDP header, and I'm returning A, and A is the total value of the length that I calculated. Same goes for TCP, but if it's port 80, I'm going to say pass, so I'm going to return the whole packet. And if it's not port 80, I'm going to just get the length of the TCP header. So what this filter does is it gives you the Ethernet header only if it's, it gives you full frame if it's HTTP traffic. It gives you the UDP and TCP headers if it's UDP or TCP other than port 80. It will give you the IP header length if it's non-TCP or non-UDP, but it is IP. If it's not IP, it will just give you the VLAN, the Ethernet header. So it's a very complex filter that you can, maybe save space on your hard disk for and maybe prevent packets from being dropped that way. So in summary, before we go over to the demo, BPF is very quick and powerful. It's bytecode actually being pushed to the kernel engine from user space, which is kind of nice. Very flexible. So learn the language, get used to building BPF filters. And it can be used for post-processing. That's one of the things I'm going to demo is how quick it is. You can check the compiled BPF filter. So once in a while, create a filter, check the compiled filter, and start learning how the filter is actually been working. And you can even write your own BPF filters if you really want to stretch out on the functionality. And my mantra always is, as long as you can calculate where the offset is of the data that you want to filter on, you can use a BPF filter. If not, then you can't. So no searching for data, no loops allowed. So before the demo, are there any questions about, is it useful? Do you think you can use it in daily practice? All right.
So, I'm trying to apply this.
Yeah.
So, what I got was either TCP dump or link dump or next if.
Yeah.
Those are the only tools that we can use to apply this.
The question is, are TCP dump, dump cap, and netsniff and G the only tools that can use BPF, right? No, that's not true. BPF is an engine that's in the library libpcap and winpcap. So any application that uses those libraries can utilize the BPF filters. And like I said, on an F5 load balancer, there's packet filters to filter traffic that comes in and out of the box. And that is using the BPF language as well. IP tables are now, it's possible to use BPF filters in IP tables. So if you want to have a host firewall on your Linux system. So there's all kinds of options. And most open source programs that deal with with PCAP data, they use libpcap or winpcap. So in all those programs, you can use this.
So, are you using just a straight editor to read this, and then you're compiling it with,
Let me show you the demo. Yeah, I can show you how it works, and then if you still have a question on how to use it, feel free to ask again. Okay. Any other questions before the demo? All right. Okay, I've got a trace file, example.sharkfest. I made it at home, so there's some home traffic in it. So I can't use it in T-Shark, so I'm going to use TCP dump. We need to have a TCP dump fest as well. TCP dump, I'm reading example. I could use it as capture filter with dump cap, but I don't know if there's any interesting traffic at the moment. So I'm just using TCP dump for the demo now. So TCP dump, I'm reading this file, and I'm just limiting the output to 10 packets. So I might want to filter on host 10.21.7.225, which is my Mac at home. And it doesn't give me anything. That's surprising. That's always fun about demos. Why isn't it not showing me anything? Oh, I know. Something's biting me in the foot. I've got VLANs at home. So this, see that you need to specify specifically where you want to look for the IP address. It's a VLAN tag traffic, so it's Control C, not working. Okay, so as you can see, it filters specifically for a certain, and I need to make it even quicker, I need to do -n for no resolving. So that's just 10 packets. Okay. So if you're wondering what this filter looks like at the BPF level, I can just say -d. And then I need to select an interface because it needs to know what link layer type I'm talking about. Because every link layer type has different positions for where the data is. If I'm using PPP, there's no Ethernet header, so it needs to look in different locations. So you tell it which link layer type you want to use, and then it can compile a filter for you. This is actually more, so if you walk this through, these both are ether types for VLAN tag traffic. Then you look at the inner ether type, if it's IP, look for the IP addresses. Then 806 is actually ARP. It's the ether type for ARP. Whenever you create a filter with BPF, if you're filtering on an IP address only, it will say, okay, I'm filtering for the IP traffic, but also for ARP traffic for this IP address. So that's extra, you get it for free, but you can skip that by saying, I just want the IP traffic. But normally, you will get ARP traffic as well. So you actually don't need this code, it's just for verification. And the same goes for Wireshark. If I, let's see, if I want to capture options. So if I go VLAN and IP host 10.21.7.225, and I didn't select an interface, see that you can't compile the filter because it doesn't know what link layer type. So I said, okay, do it on the Wi-Fi, and it's got a simulated Ethernet header, so it will work. Compile, and it will show you the same filter. So you can check it from within the GUI as well. Then the performance. Let's say I want to use this filter with T-Shark. T-Shark, I mean, read the, what's the file, example. I'm going to write it to T-Shark test.pcap.ng, and I'm going to use the filter -y host, sorry, IP address, of course, 10.21.7.20, like this. And I'm interested in how long it takes, so I'm going to put the time before. So we're going to get some coffee. I think it was quicker before. It was like 7 seconds or so. So it's, oh no, that's because no, it was without a filter. It was like 1 minute. So take your time.
Welcome if you got it.
See, it's 32 seconds. There's the real time of that. So now do the same. So I need to change my filter to a BPF filter. IP host, don't do the same mistake again, VLAN end, and it's not -y, and I'm going to name this TCP dump, and I need to change the command to TCP dump. Three seconds. So that's 10 times faster. Why? Because T-Shark reads a packet, looks at every little bit of the packet, decides what is in there, and then it starts filtering. BPF, oh, this is not IP? Okay, I'll skip it. Oh, it's not the same host? I skip it. So it's very fast. So whenever you're working on large trace files, and you can filter on layer 4 information, or you know that you can filter on stuff that you can calculate where it is, you might want to pre-filter with TCP dump before you run it into the Wireshark or T-Shark. Is that a question?
I feel that your TCP dump will be even faster than 3 seconds. I believe that is limited by your disk space. Hard disk. If you use SSD, you'll find the time will be much faster than 3 seconds.
This is SSD. Yeah, but if you look at the cap infos, it's 400,000 packets. So it's quite a big file. Can you speak up a bit, please? I've got some fans here, so I can't really. Yeah. Okay, yeah. The question is whether my system is caching the file and makes it quicker. So you expect this to be quicker than the first one run? Let's see. Let's have some coffee again. I tried that before because I had the same suggestion, so I tried it before. It doesn't make a really lot difference. Same goes. Well, it's 800 milliseconds quicker. Now, it depends on what the system is doing, but I noticed that it's almost the same order of magnitude, the same all the time. Anything else? Any more questions on? Does this answer your question about how to use it?
How much that we do in terms of making the mnemonics? Mnemonics are made within the program.
Yeah. If you start using capture filters, BPF filters, don't look at the mnemonics. Just use IP host, TCP port, ether host, all those filter. Yeah. Yeah. But I got into BPF programming or BPF checking actually more or less because I noticed that some filters didn't filter what I needed to filter. So I was wondering why does the filter not give me the information that I need? And then it's handy to look at the BPF code. Okay, it's looking at the wrong place because there are some quirks in BPF, like the VLAN offset being increasing. If you don't know that, you're surprised. And when you look at the BPF code, you can see, oh, it's looking at the wrong place, and then you might be able to solve your filter. Yeah. Good. All right. In that case, I'm going to show you the. I can. If you look on the internet for PCAP filter mount page, it will give more information than in this session, but it gives you some examples of all the filter words that you can use, because there are some advanced ones, like this one, the gateway host. I've never used it, but what it does, it will check whether your MAC address is for your gateway, while the IP address is not the IP address of your gateway. So all traffic that goes through your router will be filtered by this filter. So there's quite a few things in here. You can filter on a net. Oh, I should have put that in the presentation. That's actually a very handy filter. You can filter on a whole subnet. It should be in the presentation. You can do a port range, which I didn't show you. Since I have time left, I should add, if I do the presentation again, I should add more stuff. But I always talk quicker than I think. So look at the mem page if you want to have extra inspiration on how to use these filters. So if there's no more demos requested, and feel free if you're struggling with building BPF filters, my email is in the presentation. So feel free to contact me.
How hard would it be to write a program to extract the mask so to see it?
How?
So in other words, you know how you used to like you could watch a register and when it updates you know what the value of that register is without it. So for example, IPIP, right?
Yeah.
When you map or TCP 13 and since that. So if you show that real value, you would know that the code is correct without having to remember.
So you want to not only show the code, but have an example packet and show what it really does.
So you can check it.
That's a nice option. It's not there, I think.
When you're writing the
Yeah, but like in Excel, when you change the format of your cell in Excel, it shows you for the value that's in there how it will be displayed when you're changing it.
I haven't used that, but it sounds like it's
Yeah. Yeah, if you change the format of a cell and there's a date in there and you do a custom format, it will show you how that cell will be displayed with the custom format. Yeah.
So that way you can quickly check without having to go and being lazy. But
Yeah. Yeah, you need to write something for that. Well, how difficult it is, I'm not sure. Yeah. Yeah, you want to follow the stream, like, okay, it's not matching now because of this particular bit in the.
you're expecting an IP address.
Yeah.
Like, what the hell is that?
So it's kind of like an evaluator, like given this packet, given this filter, show me the step that the filter is taking. Interesting. Go learn to program in C or whatever language. That's always my answer if somebody asks something. No, it's an interesting concept, yeah. All right. Any more before we get some lunch? Well, in that case, thank you for listening.